Good morning. Peter Sammonds. I direct something now called the Institute for Risk and Disaster Reduction, and I just thought I'd say a few things about that in the context of this meeting, and also just acknowledge my co-authors on this, Dan Hatton and Daniel Feltham, and also acknowledge some thanks to some current collaborators, Sally Scorfield, Ben Lishman, and Mark Short. So what I'm going to talk about, when I get round to it, is the micromechanics of sea ice frictional slip from basin scale experiments. But I just thought I'd sort of start off by saying sort of where I am now in the scientific landscape, and that is this Institute for Risk and Disaster Reduction I set up a number of years ago, and I think it has relevance to our discussions here and about the type of science that we do and the type of how we interact with society. So this is our first sort of example of somebody trying to build a resilient society. The Canonbury Tower in 1509, built for the universal deluge. So when the next universal deluge came, the builder could evacuate to the top rooms and survive. And I say this is our first example of somebody trying to build a resilient society. Next to it is the front copy of our annual report, and I've just put a few copies outside as well, if anybody is interested. I'd also say that yesterday, as well as being, of course, the 100th anniversary of Finnish independence, and I think actually that probably shows some sort of storming of the Winter Palace rather than actually the Finnish Revolution itself, was actually the founding of sort of disaster as a science. There was an explosion of the SS Mont Blanc munition ship in the harbour of Halifax following a collision, and the vicar of Halifax, the Reverend Samuel Henry Price, as he was then, after spending a lot of time gathering information, ministering to his flock, then went to Columbia University and within 2 years produced this sort of founding thesis, Catastrophe and Social Change, which is very much sort of seen as the beginnings really of studying disasters as a holistic phenomenon, not simply just sort of as a physical or natural phenomenon. So that was 100 years ago yesterday, the Nova Scotia explosion. And then just say one or two things about what the Institute does. I mean, we're quite heavily engaged in what we call global challenge research. So this shows one of my colleagues. She's actually a computer scientist, and she's working on using digital technology to bring, in this case, information to perinatal women on how to sort of improve health outcomes. This is in Nepal, following the Nepal earthquake, the Gorkha earthquake. So obviously, getting information to remote communities, and obviously particularly women in particularly vulnerable position, is of utmost importance. And also we teach, these are some of our master students at one of the NGOs called Rescue Global, which sort of Rescue Global literally does go around rescuing people after disasters, but having done that for a number of years, they've begun to realize also that actually rescuing people after disasters are not really the way forward, that the way forward really is to increase resilience prior to disasters, and that's why they're engaging with us a lot now. And so that comes on to the context of my still continuing work on ice, and now this is, I think, probably done in the context of Arctic risks. So Arctic risks is one of the key themes for the Institute for Risk and Disaster Reduction. Just listed some of the people involved in Arctic risks work here in the IRDR, and also the centres involved, still obviously the Rock and Ice Physics Laboratory at UCL, which is set up, a long time ago now. The Centre for Polar observation and modelling, and also we now have what we call the London Polar Group, which is meant to be very much this transdisciplinary group bringing together engineers, scientists, social scientists, economists, and so forth. And I think that this is important in the sense that that we do our science, but I think the idea that I think the science landscape is changing. The endless frontier of science, you know, the famous 1945 report by Bush for the President of the United States, then describing the endless frontier of science, might have reached its frontier, and actually we're far more, I think, constrained to place our research in a social context now. And again, sort of talking a little bit more Arctic risk. So there's an Arctic risk. That is me in Svalbard, undertaking the Samcot safety course, where you have to cut a hole, or somebody cuts a hole in the ice. You have to leap in, and then you have to get out. Well, let me just say I didn't actually manage to get out. There was a rope around me, thank goodness, but I did learn that actually if I do sink through the sea ice, that probably pretty much is it for me. So in that sense, that was a useful educational exercise. And again, thinking about Arctic risks again, what the IRDR does, this is a report we produced a couple of years ago. We sent it to the House of Lords as part of the UK House of Parliament, as they're having an investigation into Arctic risks, and we actually examined two possible scenarios. I mean, scenarios are a very sort of productive way of looking at these things to try and account for what are the quantities that you really need to take into account. And our two scenarios we looked at, one was an under ice oil spill, and the other was probably the nightmare scenario of a cruise ship sinking off the east coast of Svalbard in international water, with either sort of British or German tourists on board, with the boat sort of chartered sort of from a Moroccan shipping company, something like that, some sort of nightmare scenario where there's little responsibility for who actually has sort of, you know, direct ultimate responsibility for that, and of course very limited resources to mount rescues. But I think, you know, these are actually, in a sense, very, you know, quite, well, that's why we'd run them, to be quite realistic scenarios for the sorts of risks that might be faced in the near future in the Arctic. And I think it's probably sort of a focus of sort of a reminder of sort of some of the things that we really should be interested in. And again, just to continue with the Institute, where also we work with Indigenous people. There's a program called Many Strong Voices run by my colleague Ilan Kelman, because of course people live in the Arctic. It's not just there for us to do our science and engineering. So sort of moving on to that sort of moving on from the Arctic risk context, just wanted to say something about why being here in the Isaac Newton Institute for Mathematical Sciences I think is a tremendous privilege. So this is just one of the slides from my MSc lecture course on earthquakes. This is just saying about the theory of the seismic source. So you have, I'm sure familiar to many of you, the idea of an equation of motion for a continuum, and you need to solve that to understand the earthquake source, and you solve it in terms of displacements using Green's functions. And at this point I usually ask my students, well, how do you solve this? Of course, most of them sit there sort of open mouth without a clue, and so I then come up with the answer. You ask a mathematician. And I think, you know, this is actually, you know, I think something that's, you know, a really important thing. You know, the mathematicians have their expertise, they have their knowledge, and I think it's really up to us very much to engage mathematicians. I hope this is what this meeting can do, to say, you know, we have important questions which are important in terms of our science. We think they're important in terms of their societal impact. For instance, again, if you think about sort of Arctic risk scenarios, and actually we really do need and welcome the collaboration of mathematicians in answering these questions. And again, I'm also a bit involved in volcanology. This is an image of me doing a picture when I was doing some field work up on Mount St. Helens. And just to mention, I think the transformation that occurred in volcanology because of the collaboration between a mathematician, Herbert Huppert, and a volcanologist, Steve Sparks, who seriously advanced the understanding of volcanology over a generation by this collaboration between an observational, empirical earth scientist and an applied mathematician and theoretical physicist. So I think when this works well, I mean actually the gains can be enormous. So can we interest mathematicians in ice fracture questions? I guess is a question to ask. So this is an image I made. This is Isaac Newton as drawn by William Blake, probably as equally as famous as this image. But of course, William Blake very much regarded Isaac Newton not so much as being part of the Enlightenment, but as being part of this infernal trinity, actually sort of designed to separate humans from God, and I guess you might say humans and society and detached science from society. And so I think it's quite interesting that go to the British Museum, the image of Newton outside the British Museum is actually a sculpture taken from William Blake's wood print, rather than sort of one of our more traditional images of Isaac Newton. And again, I think the messages again that though it's good for us scientists to talk together, but actually we do need to think about our broader societal engagement. So somebody said that we don't sort of introduce things enough, so I'm spending lots of time introducing things. And so I thought actually let's go back to some of the beginnings. I mean, why are mechanical models needed? And my sort of rule of thumb is that for earthquakes always occur in regions of lower probability seismic hazard. And so, for instance, this is the seismic hazard map in terms of peak ground accelerations for the island of Hispaniola, with Haiti on the western part of it. This was the risk map for Haiti prior to the 2010 earthquake, and of course, as you can see, we have Port-au-Prince is actually in the lowest zoned risk region of the island. So of course, that is where the earthquake occurs. I think if you look in California or the Persian Gulf or Central Asia, you'll find almost always the same thing. The earthquakes occur in the region of lowest probabilistic seismic hazard. And of course, this doesn't occur for areas as well. This occurs for magnitude. If you look at the Tohoku earthquake, a magnitude 9 earthquake, of course, off the coast of Japan in 2011. RMS, Risk Management Solutions, one of the companies who actually modeled these things, didn't actually even have a model which said there could be an earthquake above magnitude 8. So this is sort of why I think we need to have mechanical models. Again, looking at this map, I actually set this as a master's student exam question, which thankfully they all got right. But you can actually see the major faults actually going straight through Port-au-Prince, and why on earth the faults are going left to right while the contours of the hazard map are going up and down is anybody's guess. So this was obviously a risk assessment done without any understanding of the mechanics of faults. Again, collaboration with mathematicians. That a few years ago, Ben Lishman and I, we did some experiments, Danny FelthamWe, on rate and state friction, and we came up with an empirical rate and state friction law for sea ice, and it's published. and just say the advantages of things like rate and state friction. It's a very simple law, just a few parameters. And again, because geophysicists, applied mathematicians have actually developed the theoretical framework to include rate and state friction in large-scale mechanical models, because of course this is actually how modeling of earthquake faults is now done. I mean, your hazard assessment, for instance, if you come off California, is far more likely actually be based now on the rate and state friction laws than it is purely on some sort of probabilistic seismic hazard assessment. But actually, this framework exists. And so I'd also say that, again, for applied mathematicians who might be here, that really there's something that can be done very, very easily by just taking simple empirical laws and which we as experimentalists can work out, and fitting them into a better framework. And I think obviously another example of that of Erland Schulson and his development of anisotropic cracking theory in sea ice, and Danny Feltham and others sort of implementing that into large-scale Arctic Ocean models. But I'm not going to talk about rate and state friction. I just wanted to flag that as, again, somewhere where actually an existing empirical law could be put into a broader mathematical framework. But to move on more to posing the question of modeling the Arctic polar pack, and this is a radar sat image of Rong Kwok. It's very old now, probably like 15 years old, but it still very much sticks in my mind, of showing the polar pack involving these large-scale shear displacements, which in my mind really characterize the dynamics of the pack. And the idea then that actually you have tensile fracturing, of course, you have compression causing ridging, but actually it should be very much the deformation and sliding on these lineaments, which actually in many ways look very much like crustal faults, which should be controlling the large-scale dynamics. And there is, of course, a conceptual framework for that, shear fracture mechanics. So here we have a crack sliding, and we have compression and tensional points to it. But I think that the point about shear fracture mechanics, and that probably a mathematician will tell me I'm absolutely wrong, but my understanding of the formulation of shear fracture mechanics is that it can be applied as much to a crack as it can to a sliding surface, or vice versa. So frictional slip can actually be characterized by shear fracture mechanics. And in particular, what's called the slip weakening model. Here we have shear stress plotted against slip displacement, where we see that as surfaces slide, we have an initial shear stress, we reach a peak shear stress, we then have a breakdown to a dynamic frictional value over a length, the critical slip displacement, releasing, of course, the failure energy, the critical energy release rate. And modelled sort of more succinctly by that, and the idea that progressive failure that occurs at stresses well below the shear material failure strength. The shear displacement occurs in concentrated bands. As we saw from the radar sat, the shear stress decreases with slip. We can employ concepts of fracture mechanics to describe this. It necessarily introduces a characteristic length scale into the material description, and this is a way of unifying the theory of slip failure and the failure of intact materials. Slip displacement is independent, and essential variable time dependence is important, and is capable of explaining dynamic rupture. And there are experiments that show this. I mean, these are experiments conducted by Mitio Naka in the Earthquake Research Institute and Earthquake Research Institute at Tokyo University, showing sort of experiments where you slide one block against another. You have strain gauges along the length of the sliding interface, and then you can see how the slip nucleates and propagates with time. So this is a schematic actually taken from experimental results from that sort of frictional sliding experiment in the lab, where you have a distance along the fault plotted against time. You're using the strain gauges to measure the instantaneous slip, and you see that you have a nucleation regime. And once the nucleation length reaches a critical length, the critical size of nucleation zone, then the slip now propagates dynamically. And in a sense, it's very much akin to the nucleation and propagation of a fracture in more sort of classical fracture mechanics tests. So our ideas for looking at Arctic Ocean dynamics controlled by tensile fracture, frictional stick slip. The compression is important for ridging and local contacts. But then, of course, the question is, what is the right law for sea ice friction? Is rupture dependent upon slip displacement? Is there a characteristic length scale associated with sea ice dynamics? Can we apply fracture mechanics? And for this is what we need to investigate. And what I'm going to say today is very much sort of now published, that we had this volume come out just under a year ago called The Microdynamics of Ice, written with a paper written by Dan Hatton and Danny Feltham, based actually on some experiments in Hamburg, the ship testing station. This is before it was refurbished, where we have a ice sliding sheet, very much like Mitya Narka's laboratory experiment of rock fracture mechanics, but now this is done on floating ice in the saline ice in the ice tank. We have a couple of mathematicians being very useful there, actually soaring up the blocks to make this the sliding. And as you push the central block through the two confining blocks on either side, we saw this sort of very characteristic stick-slip irregular cycling of stress. So this is where shear stress is now plotted against displacement, slip displacement, and we see this irregular stick-slip cycling. And just sort of focus in on a single stick-slip event. This is now the shear stress plotted against time for a single stick-slip event. Of course, surface roughness is important for any frictional property, so we cut out blocks from the sliding surface to measure the surface roughness. This is a 3D profile of it, and also a 2D profile as well. And our analysis of this sliding surface, which we published, or Dan Hatton published in Phil Mag in 2009, is of a surface that can be characterized as a fractal surface. So even if the surface is not fractal to begin with, because it's saw cut, once you've slid it, that actually creates a fractal surface. Again, just conceptually what that experiment looks like, you have a moving plate between two side plates. So we apply a side load, and I say it's very much the classic double direct shear test, which has been performed for decades in the lab, performed in the ice tank. And this shows more specifically the experimental setup, showing at one end we have a pusher plate to apply the load. We have our potentiometers, which measure our slip displacement. We had rosettes of the BP's mercury pressure transducers, giving us the local measurements of stress. We had strain gauges on transducers in the ice, and we also measured acoustic emissions as well to monitor the cracking activity as our experiment went ahead. And then at the bottom we had these floating wooden panels where we could apply a side load. So this is an experimental result, so showing plotted in on the three axes. We've got shear stress plotted against distance and plotted against time. So we have the slip propagating both in distance and time, and what we have here are the stresses recorded at positions down the sliding interface, and you can see that the stress first of all increases on our first two position locations before then the slip propagates down the length of the fault. So again we sort of have a nucleation regime and a propagation regime, very much like Mitonaka's rock mechanics experiments at the Earthquake Research Institute. And then just sort of to characterize that, we've got time here plotted against distance for that experiment, showing a slowly increasing shear stress in the nucleation regime up to the breakdown slip, and then high speed propagation, faster than we probably actually could measure it, but certainly higher than 56 meters per second. Looking at a single stick slip event, again this is now experimental data on the left hand side with the schematic on the right. It shows the various features again, the increase of shear stress from an initial load up to a maximum, a breakdown to a residual level over DC, the critical slip displacement, stable sliding, and then re-strengthening as you're about to go into the next stick slip cycle. And in terms of shear stress against velocity, this again shows those numbers, those Roman numerals correspond to the phases of deformation of the previous experiment. And I just compare those to now the idea that you have the increase to the maximum shear stress, acceleration in phase 2, and then deceleration in phase 3 until we come down to a residual level and re-strengthening. And the shear rupture energy, of course, just be related to the integral of this, or the breakdown shear stress times the critical slip displacement, and where you've got gamma is some a parameter which depends upon the particular geometry. So again, so it looks like we can apply fracture mechanics to the ice slip propagation problem, and again that is something I think which can be taken up. The scaling, so this is the scaling between DC, the critical slip displacement, and the breakdown zone size. If you look at this, the ratio of those is about 10 to the minus 3, which is very interesting. The ratio of those two parameters in earthquake mechanics is also 10 to the minus 3. But I'm not going to particularly pursue that further, apart from take one thing from that, but actually look more to micromechanical modeling and the idea that, okay, so we could develop a fracture mechanics model of friction for ice, but actually what does it mean in terms of the microphysics, and therefore actually trying to develop a model for our large-scale Hamburg ice tanks actually based on microphysics. And the idea here, you take two surfaces, you push them together, the asperities will deform ductilely, they'll deform elastically, and then you slide them past each other. Again, the asperities will deform elastically and ductilely, and also have brittle fracture. And of course, there could, if you've got surface melting there, you also have the lubricating effect as well. So just sort of zoom in what an asperity contact looks like. We have this sliding these two asperities past each other. We have two radius of curvature, because we're dealing with this, so this two-level fractal surface. We have melting at the asperity contact and expulsion of the melt water. We have D0, which is the slip for the asperity to actually clear each other. And we find that we have four key dimensionless quantities, which we then have to later incorporate into our micromechanical model. We call them the melt water expulsion displacement, the contact breaking displacement to actually break the contact, the shear layer thickness, and also the normal asperity strain. So we can build up a friction law then by just saying the shear stress is proportional to the shear stress to break an asperity times the area fraction of asperities on that surface given by F. And just note, so we then this conforms, to our basic idea of a friction law, that the shear stress is proportional to the normal stress to an exponent n. Of course, with n equals 1, we have Amundsen's law. For n equals to 2/3, we have Archer's law, which of course necessitates the idea that the coefficient of friction, so to speak, is dependent upon normal load. And we calculated, I say in 2009, that actually for a two-stage fractal distribution, n is equal to 26/27. So n can sort of be anywhere between about 0.3 and 1, depending on your particular model for the surface asperity distribution. So our experiment shows slip weakening occurs, so we have to introduce slip weakening into our model. So here this shows how the shear stress degrades with slip. So here we have the dH is the slip displacement here, M is just an adjustable parameter, and D0 is the characteristic displacement for an asperity contact. So we have lubricated hydrodynamic friction, of course governed by the usual law, dependent upon the slip sliding speed, viscosity, and the fluid layer thickness. Then we have to decide how we're going to actually construct our micromechanical friction law, because obviously we could choose these sort of in an almost infinite number of ways, and we decided, or Hatton actually came up with the idea, that the friction really needed to maximize the displacement for normal deformation and minimize the stress for shear failure. So applying that criterion, this picks the largest value for real contact fraction, the elastic or ductile, and the smallest value for the shear strength, say the ductile shear strength or the brittle shear strength or melting lubrication. Then you can rearrange some equations. Quantitatively, then the frictional melting model predicts a shear strength, which I won't read out, but of course now it is dependent upon those microphysical properties, the thermal conductivity, the specific heat, the temperature melting, which is of course pressure dependent in itself. Which then brings us on to an expression for the shear stress in terms now of our fractal asperity distribution, because we've both modeled it and measured it to be fractal in nature. The melting lubrication stress and slip weakening. We understand what our real contact fractions for elastic deformation are under normal load and under a ductile deformation for normal load, which we calculated in 2009. Then we can plot our model here against experimental data collected from our ice tank experiment. So what we have here is our line, which is simply a microphysical mechanical model, and our points, which are actually points measured from 22 experiments, many millions of data points, to compare that obviously within a constrained range. And I wouldn't say it's brilliant, but we do see that in many ways the micromechanical model does capture some of the key features of the observed macroscopic behavior. Let's say an increase in shear stress, a rapid breakdown in stress, and then slip dependent and then slip dependent weakening. So summarizing all of this, so we propose therefore that we have got a micromechanical frictional model which could be applied on an Arctic scale. We have to incorporate these adjustable parameters. These adjustable parameters mostly actually could be measured in principle, though we obviously derive them from our experiments. And to note that friction is predominantly quasi-cyclic slip behavior for our experiments. It's characterized by slip weakening. It follows Archer's law with n equals 26/27. We find that surface asperities deform elastically under normal load, but the interface fails in shear through a process of frictional sliding, localized surface melting, and hydrodynamic lubrication. We're continuing with this work, so we're also working on the buoyancy as well, because we think it's also important to large-scale experiments actually in the Arctic itself. We've done a hold-time experiments there. This is published by Sally Schofield in POAC in 2015. And again, this is now with a gouge between the sliding surfaces, showing two distinct regimes, a frictional regime and a consolidation regime at long hold times. And again, this year we are back in HSVA. This was in their large, now refurbished tank. And again, looking at this on a more sort of detailed experimental scale. Again, a very, very sort of classic rock mechanics double direct friction experiment with a fault gouge. But this time the fault gouge are floating fragments and discs of ice. So in this sort of quick tour of models, I've actually gone through 3 different models. The idea that there is a empirical rate and state friction law for sea ice, which is fully serviceable and could be taken up and put into large-scale models. We've seen how there can be a slip weakening fracture mechanics model to describe slip propagation in ice, and we've developed also a micromechanical model, a microphysics model from first principles, which at least captures some of the observables that we see in the Hamburg ice tank. So just sort of conclude, the idea of working with compatible models and coming back to Newton. Of course, Newton was also a very famous alchemist, so of course, as well as developing the laws of motion, understanding force, he spent a great deal of time with his experiments in alchemy, and so I think Newton was somebody who actually could work with incompatible models. You might say the 3 models I presented in some ways are incompatible, and is there a right answer? And actually, I think that we have to use models as we find them for the purposes that we want. And just a final note from famous economist John Maynard Keynes: Newton was not the first of the age of the reason, he was the last of the magicians. So that I shall finish. Thank you very much.
Interesting presentation. Just thinking back to the presentation that I gave on this slurry layer that develops during ice crushing, whether it's ice crushing against a table, glass, or ice, which is your case here. it's very likely that there, besides some fracture and slip and so on happening on your asperities, that in fact there is crushing happening there, and that would imply that the slurry layer is present rather than just some fluid. Now the slurry layer is a wonderfully lubricating material. However, as soon as you slow things down or take the pressure off to the extent where there isn't crushing anymore, it becomes a glue. In fact, in crushing experiments, when you crush ice against ice, at the end of this, when you pull things away, they're stuck together. So that, you know, would be sort of part of the picture of a stick action.
No, I agree with you, and I think with the introduction of this rubble as well, we're beginning to try and look a lot more of that whole idea actually of the mechanics. I think we started off as simply as we could, and that's where we started, but it's not where we intend to end up.
Sorry. So you said that you have a slip weakening behavior, but it seems that you have an equation where you have a velocity strengthening behavior, no?
Yeah.
So how could you have an instability if you have a velocity strengthening behavior?
Interesting. I mean that. I slip weakening is an observable, and we can't model our results without introducing a slip weakening into the process. I mean that there has to be re-strengthening, if you mean that, because if you have to go into the next stick slip cycle, and without that re-strengthening, you wouldn't get stick slip. So I think both of these have to be there. I say we haven't developed it in those macro modelling terms. What we've moved on to is trying to develop this micro physical model instead. So we haven't really looked back at that yet.
Because in rate instead friction, I mean, if you have velocity strengthening, it is stable and can only be unstable if you have velocity weakening. So I do not catch yet what are the difference between what you are developing here and.
So I mean, the rate and state friction law, as developed, backed by Ruina and Rice and so on, is incompatible with a slip weakening model. That is true. Matsuhira at Tokyo University actually did try and reconcile these two models by putting together the slip weakening model with the rate and state friction law. But I agree that these come from different conceptual frameworks, and I was trying to say that actually we do have incompatible models here.
If I understand correctly, Peter, I'll put it differently. Correct me if I understand incorrectly. When one measures the coefficient of friction, of course, we're always dealing with this issue of jerky stick-slip behavior, which itself is a phenomenon that's not been explained. But leaving that aside, when we speak of the relationship between the shear stress and the normal stress acting on a body, there are two regimes of behavior. When the body is sliding slowly, there is what we see velocity strengthening. This goes all the way back to Barnes, Tabor, and Walker in 1972, where they slid ice on granite. And if you slide ice upon itself, you have that velocity strengthening, where the coefficient of friction goes up, as you said. Beyond a certain point, one gets velocity weakening, where with increasing velocity, the coefficient of friction decreases. And of course, at higher speeds, still you get hydrodynamic effects when you get strengthening again. Now, when you're speaking here of the slip weakening, you're not referring to the velocity weakening.
No, I'm referring to the slip dependence.
Just the displacement
Yes.
from the high to this low point over this distance delta d sub c.
That's right, yeah.
So that's a transition from what might be considered the static state to the more steady state of sliding velocity.
Yeah.
That's what you have in mind.
That's right, yeah. So again, these are different models, and I haven't put them all together yet. I mean, in terms of the microphysics model, I mean, we probably publish in Phil Trans that we do see these transitions with velocity, for instance, our microphysical model with the coefficient of friction, as you say, when melting lubrication coming in. So the microphysical model does capture many of those, but not all of the observables.
Yeah, I would like to hear your opinion on measuring stick slip, because I have this issue with that in the stick stage, when we're loading a system, in the stick stage we're storing energy, elastic energy, into the sample and into the measurement system. And then when the slip starts, this elastic energy is released, or part of it is released. Nothing is perfectly stiff, so there's the effect of the system. Measurement system is there always, but then also the volume of the sample we are studying comes into picture. And when the elastic energy stores into a volume, and then the friction is related to areas, I think the experiments always have kind of things that are built into each individual experiment.
I mean, you know, that is entirely true. I mean, the stick-slip phenomenon is a phenomenon of the system and not of the material. I mean, that's absolutely true. I mean, you know, we looked at in earthquake mechanics as well, exactly the same sort of issues. I mean, but the observable is obviously in the crust we have stick-slip. You know, the observables are in the Arctic we have stick-slip as well. And again, our analysis from 2009 was that stick-slip was the dominating effect. But yeah, it is a system response, not a material response.
May I ask one more question for you? When you related the shear stress to the normal stress to the power n, and you referred to Archer as saying n was 2/3, and then in some of your early work you showed, yes, n seems to be about 2/3. Others come along, including ourselves, and we find, no, we find n is close to, Coulomb might have said, n being 1. The regime, I think if I have it correct, that you explored was relatively high normal stresses, 5 to 200 MPa, and others, including ourselves, were much lower, much lower. So is one to understand that this n value could well depend on the magnitude of the normal stress?
I mean, the Archer formulation of friction in 1953, I think it was. You know, that was his point. That actually the coefficient of friction is dependent upon normal stress. So I think, you know, the experiments you referred to when we found n is equal to 2/3. But I know I did a few experiments. Obviously, Martin Rist did quite a extensive range of experiments and came out with this 2/3 value. Were all at high normal stress. In terms of the micromechanical model, which we developed here, we found n to be 26/27, and that fits the ice tank data fits that model very well. So you can say might say it's very close to 1, but there is a small normal stress dependence upon the coefficient of friction.
Is that because the coefficient in that model is defined simply as the shear stress divided by normal stress, as opposed to the derivative of the shear stress divided by delta tau over delta sigma, because they are very different.
No, that is true. If you're thinking of the Coulomb frictional formulation where you have a cohesive term as well, that is true. That is a different formulation. Yeah.
So it's just taking the simple ratio of shear divided by normal.
Yeah.
Now that can be a little misleading in terms of the friction coefficient.
Just going back to the crushing aspect, the higher the normal forces, the more crushing will be happening on asperities and whatever sort of non-flat surfaces that are making. So that may be a factor in there also.
No more questions. Thank you once again.
Thank you.